So another thing that you guys have asked is, why are low pressure systems associated with clouds, or how do clouds and precipitation develop from low pressure systems? So I'm just going to go ahead and orient you to this image here. You have our sun, it is daytime. And then we have three surfaces, a grass surface, a sandy surface, and another grass surface. The reason I've done this is I've given a reason for there to be differential heating. Now, go back and review the previous video if you're not sure what that means. But as a summary, our grasslands are going to heat up slower than our sand, which is going to heat up quicker. So we can see that here, our temperature over our grass is about 20 degrees Celsius, and our temperature over our sand is going to be 30 degrees Celsius, so it's warmer. And when that air is warmer, it is also less dense. So I've gone ahead and taken the liberty of drawing some theoretical columns of air above each of these different surfaces. You'll notice that right now at the beginning, they each have 10 air molecules. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They all have 10. Now we're going to go ahead and go further up in the atmosphere. And we're going to look at this level to see what exists above this level. We have one air molecule here, two here, none here, right? So remembering that pressure is the weight of an air column above a certain point, what is the pressure at 3 kilometers and the left compared to the center? We have 1 versus 2 in the center, so it's lower, right? So let's go ahead and denote that. What about this right column? It's also lower than 2. 0 is less than 2, right? So we'll do an L here, and then we'll put an H here. Remember that pressure gradient force pushes from high pressure to low pressure. This is our simple wind. We're going to ignore other forces. Now remember, wind can physically move matter. So what's going to happen is it can physically move these air particles. So, one's going over here, and try that again. One's gone over here. Let's move those air molecules from higher in the atmosphere over the desert or the sand to those grassy areas. Now, let's see what the pressure is at the surface now. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over this left column, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over this right column. But over the center column, we only have 1, 2, 3, 4, 5, 6, 7, 8. So at the surface, we have 8 here, and we have 11 on our sides. So what that means is, comparing the 3 columns, our lowest pressure, our lowest weight, is in this center column. And our other columns have higher pressure at the surface. Again, remember, pressure gradient force pushes from high to low. And that is our wind. But let's think about what happens once the wind gets back here into the center. We have wind coming together. What happens when it reaches the center? What's going to happen? Is it going to push past each other? Well, it can't, right? Because let's just say they're equal forces. If we have 20 miles an hour pushing from the left to the right, and 20 miles an hour pushing from the right to the left, and they meet in the center, what can happen? Can it go into the ground? Can we get air headed directly into the ground at the surface? No, because there's a barrier there, right? So what has to happen? It has to go up, right? When we have air converging, it has to go up, it rises. You can also think about this as like a vacuum, right? There's been a vacuum created up here, and so the atmosphere is naturally going to want to fix that by moving particles up to replace that vacuum. So That's what actually happens. We get rising motion through this air column. Whoops. Let's try that again. Here we go. Now, why does that create clouds? I'm going to go ahead and mark a few kilometers on here. So we've got 1 kilometer here, 2 kilometers here. I've already got 3 kilometers marked. And we'll get 4 kilometers marked here. Now, if you need a review on lapse rates and stability, please review the notes from last unit. But we're going to do a simplified version of that here. Our temperature at the surface is 30 degrees, and our dew point is 20 degrees Celsius. So that means we're not saturated, right? Our temperature is warmer than our dew point. So if we start at the surface at 30 degrees, here, we'll make this our air parcel. Make it pink. That's our, whoa. Try that again. Wow, apparently I'm really bad at drawing ovals. All right, you know what? Our air parcel is going to be a box now. Okay, never mind. Now it's an oval. All right, so it was originally 30 degrees Celsius, and we're going to move up to 1 kilometer. Since it is not saturated, which lapse rate are we going to use? The dry or the wet? We're going to use the dry. So if you don't remember, the dry adiabatic lapse rate was 10 degrees Celsius per kilometer. We've gone up 1 kilometer, so we're going to go down 10 degrees Celsius. So 30 minus 10 is 20. So our air parcel now has a temperature of 20 degrees Celsius. Our dew point is 20 degrees Celsius. That means we're now saturated. What does that mean? If you need to go back and review your notes, this is a good time to do so. But when saturation occurs, we also start to get condensation. When condensation occurs, we start to form clouds. So what that means is at 1 kilometer, we start to see clouds form. Now, if we kept rising, we'd be rising at the saturated rate, which is only about, simplified, 5 degrees Celsius per kilometer. So if we go up to 2 kilometers, let's see if we can draw an oval. Nope, we're going to do a square and it's going to turn into an oval. Yep, don't know why it's doing that. We'd be going down 5 degrees Celsius. So we're at 15 degrees Celsius at 2 kilometers. You can keep going. Now again, review the notes from last unit. Our parcel is only going to rise if it is warmer than the environment. We'd need like a weather balloon launch or something, or satellite readings to tell us what the environmental lapse rate is. But as long as it is warmer than the environment, it will keep rising and it will keep condensing and we will keep getting clouds. Now, if the water vapor in the clouds gets heavy enough and it overcomes this upward pressure gradient force by the force of gravity, it can start to rain. And that is how we get precipitation. So, as a summary, our differential heating, due to specific heat differences, leads to a temperature gradient, which leads to a pressure gradient, which leads to wind. Air converges into the low pressure system, and that air is forced to rise. As air rises, it cools either at a dry lapse rate when it is not saturated, or at a saturated rate when it is saturated. And when it is saturated, it can condense into clouds and precipitation. That is it. I hope that was helpful. If not, you know where to reach me, either at my email or in the forum.